In this video, we're going to talk about the three big existence theorems that we have for calculus. And the three big theorems are the intermediate value theorem, the extreme value theorem, and the mean value theorem. And the thing about existence theorems is they just guarantee the existence of something happening. They don't actually tell you how to find it, but they would just let you know whether or not something will occur over a given interval. And we're going to start with the intermediate value theorem. And so the intermediate value theorem, the abbreviated IVT, if a function is continuous on a closed interval from a to b, then f is going to take on every y value between f of a and f of b. And basically, let me pull up Desmos to make this a little clearer. So I have here graphed a polynomial function, but we're looking at two endpoints of an interval. So from the far left here to the far right, and I have shaded inside of here. And basically, within that interval from the far left point to the far right point, every single y value would have to be accounted for because we're continuous. So no matter what I have, so if I start at the top of the y value, it could be because the top of the function has a y value of 1, and actually let me adjust this bottom one. Let me go from 1 to -3. So because the top y value is, or the left endpoint has a y value of 1, and the right endpoint has a y value of -3, and we're continuous in between those, every single y value has to happen in between those two x values. So every y value has to occur between x is equal to -2 and x is equal to 0. That's what the intermediate value theorem tells me. And so let's apply this a little bit in context. So I'm going to look at this graph over here on the left-hand side. And we start with, is f continuous on the interval from a to b? So I look at x is equal to a, and I follow the graph. I don't see any breaks in that graph from the time I get all the way to b. So yes, the graph is continuous on that interval. And is k, so y equals k, somewhere in between f of a and f of b? Well, f of a is there, f of b is here, k is somewhere in between them, so yes it is in terms of the y value. So in this example, if a is less than c is less than b, so if there's some c value in between a and b, then there are how many c's such that f of c is equal to k? All right, so here is the line y equals k here. Now, the intermediate value theorem only guarantees the existence of this happening one time, but since I have the graph when I look, how many times will the function equal that in between there? Well, we see it 1, 2, 3 times in that interval, so there's 3 different x values in between a and b such that the function has that y value. Now let's look at the intermediate value theorem a little bit differently here. So explain why there must be a c, well this is an x value, such that f of c is equal to 6 for f of x is equal to this rational function on the interval from 5/2 to 4. Okay, well looking at the rational function, we know that f is not continuous at x is equal to 1. However, that does not include our interval. We are continuous from 5/2 to 4 because 1 is outside of this interval that we're looking at for x. So what I would need to do, since I'm continuous there, is to figure out what are the y values at those two x values. So what is f of 5/2 and what is f of 4? And so we get the y values for those two x values on the endpoints of the interval. F of 5/2 is 35/6. F of 4 is 20/3. And so why does there have to be an x value such that there is a given y of 6? Well, since we're continuous on the interval, that means that every y value in between 35/6 and 20/3 has to occur. Well, 6 lies in between those two numbers, so 6 must happen at least one time, and so this is because of the intermediate value theorem. The next existence theorem is the extreme value theorem, and I'm going to abbreviate that as EVT. So the extreme value theorem is kind of a continuation of the intermediate value theorem, where it says if we have a function continuous on a closed interval, so it has to be, note, has to be a closed interval, and it has to be continuous, then the extreme value theorem guarantees that f will have both a minimum and a maximum over the interval. Now, something to keep in mind is that a function technically can have the same y value as both its maximum and its minimum. We can have, if you had a horizontal line, technically every y value on that line is both the maximum and the minimum at the same time. When we're looking at the extreme values over a given interval, we're often talking about an absolute maximum or a minimum. We're not talking about relative or local minimums. We're talking about what is the absolute biggest y value on an interval and what is the absolute smallest y value on an interval. And so it's important to distinguish between those two. So let's look at, we're going to work here on the left-hand side with the absolute extrema. So remember, absolute extrema are the absolute biggest and smallest y values on the interval. And we're looking here at this graph. So find the absolute extrema of the functions on the given interval. So for a, b, and c, we're going to use this graph right here. And so we're looking on the interval, in this case, from -4 to 0. Now, this is a closed interval. From -4 to 0, this function is continuous. And so I want to go find the absolute minimum and the absolute maximum. All right, well, when we're talking about the extrema, we're talking about y values. So the absolute smallest y value that I see here is when y is equal to 0. The absolute tallest y value here is at y is equal to 2. Now let's look at part B. Part B, all right, so from the half closed interval, from -2 to 0, what is the absolute max and the absolute min? So the absolute max, absolute minimum, and we try to identify what they are. And so we're only looking from -2 to 0, but I don't include the 0. So we have an absolute max here. The absolute max is going to be at y is equal to 2. The absolute minimum, now we don't include that endpoint there, so we actually don't have a true minimum. All right, part C, we're going to look at the open interval from -4 to -2. Now we don't include the two endpoints there, and we want to do the same thing. What is the absolute max and the absolute minimum? Well, if I'm looking at that interval, the absolute maximum and minimum are both open circles. We don't have actually true defined values for the max and the min, so there are no absolute extrema on those intervals. And lastly, let's look at part D. So we have the closed interval from -4 to 0. So from -4 to 0, and I want to find the absolute max and the absolute min. So we have a closed interval this time. So we have closed endpoints. All right, let's start with the absolute minimum. So the absolute smallest y value on the interval is 0. The absolute tallest y value, well, that would have been 2, but I have an open circle right there. And so we actually don't have an absolute maximum. So looking at A, B, C, D, what has to happen graphically for the function to have both a maximum and a minimum? Well, it has to be continuous on a closed interval. And that's what the extreme value theorem tells us. Now we're going to look at another type of extrema, and those are relative extrema. So relative extrema are not actually the global or the absolute maxes or minimums. They are looking more locally. So if I'm looking around a certain x value, and f of c is going to be called a local maximum if relative to x equals c is the largest y value around it. Not on an entire interval, but just around the number. And likewise, x equals c will be the location of a relative minimum or a local minimum if on the open interval containing c, f of c is a minimum, meaning just right there around it locally, it is the smallest y value. And a lot of times you can identify these by having some kind of turning point. Now let's look at this graphically. So identify the relative extrema from the graph. So I have a relative extrema, I have a relative max, and a relative min, at x is equal to 0, and a relative minimum at x is equal to 2. Now the y values on those cases would be at y equals 0, respectively, and y equals 2. Now, what is the value of the derivative of each of these? Well, at our turning points, our relative extrema here, we have horizontal tangents at relative maxes and minimums for polynomials where I have those turns where I go from increasing to decreasing. The derivative of, say, y prime is equal to 0 at those 2 points. Now, let's look at the absolute value function. What does it have a relative extrema? Now, the absolute value function actually does. It has a relative extrema right there at the elbow, at the point of the v. So this one has a relative minimum at x is equal to 1. Now, its corresponding y values at y is equal to 0 if I need to know that. Now, keep in mind this. Not all relative extrema are nice and smooth and rounded turning points. In this case, we see the absolute value has a sharp turn, but the sharp turns can still be classified as a relative extrema. What is the value of the derivative here? Well, the derivative does not exist there because it's not differentiable. It's not differentiable here. And it's not differentiable because it's not locally linear. So you could say that the derivative doesn't exist at that point. So what do we have to have, or what is needed in order to have a relative extrema? Well, what we have to have a relative extrema is we have to have what's called a critical point, and where the derivative, y prime, has to equal 0 or has to be non-existent at that point. And those are how we can find x values that would be relative extrema. Now, to summarize what we just talked about, relative extrema, relative maximum or minimum will happen at a critical point. Now, here's the thing. Just because I have a critical point does not mean that I'm guaranteed to have a relative extrema there. However, relative extrema will only happen at critical points. So critical points are where the derivative equals 0 or the derivative is undefined. And so let's look graphically here at an example to try to identify where I may or may not have some kind of relative extrema. So going through here, and we're trying to identify, it actually wants both relative and maximum, or relative and absolute extrema on the interval. So this first, now it says, looking here graphically, this first point, which I actually don't even have labeled for an x value, that would be my absolute minimum there. Now, the absolute maximum would be the actual tallest y value of the function, so that would be my absolute maximum. Everywhere else would be where I have relative or turning points would be considered relative extrema. So I have a relative max or a relative min. So if we had a graph, it's going to be pretty easy to identify what's our relative max or min, what's the absolute max and min. But what we're working towards is being able to identify the location of these points without having a graph. And so how we would find our relative and absolute extrema of a function. First thing you'll do is find the critical numbers on the open interval. So you're going to take the derivative. We're going to set the derivative equal to 0, solve for x, or figure out the values that make the derivative non-existent. Once you get the critical numbers, we're going to take each candidate for our critical numbers, and we're going to plug them and the endpoints into the function, and then we're going to label them in terms of the smallest, which would be my absolute min, and my largest, which would be my absolute maximum. So, looking here at this first function, I want to find the absolute extrema. So the absolute biggest x or biggest y and smallest y value of the function on that closed interval from -1 to 2. We'll start by finding the derivative. So the derivative of f is going to be 12x to the third power minus 8x. Now, to find our critical numbers, we see what x values would make that non-existent. Well, our derivative is continuous for all real numbers, so we're going to figure out what makes it equal to 0. And so what I would do from here is I'll take out my GCF. the factor, and we can take out a 4x. So take out a 4x, and we're going to end up with 3x squared minus 2 is equal to 0. And then we work and try to solve from here. So this would give me x is equal to 0. And then we would have x squared is equal to 2/3. And I would take the square root of both of those sides there. And that would give me the absolute value of x is equal to the square root of 2/3. And I got two possible values here. I could have x could equal positive or negative square root of 2/3. And so those are my critical numbers. My critical numbers are at when x is 0 and x is equal to positive or negative square root of 2/3. Now I'm looking on this interval where I go from -1 to 2. Well, from -1 to 2, we have all of those critical numbers are candidates. So what we need to do is we need to figure out what the function's value is at -1, what the function's value is at negative square root of 2/3, figure out what the function's value is at 0, what the function's value is at positive square root of 2/3, and what the function's value is at 2, and then we'll figure out what the biggest and what the smallest values are. Okay, so we've plugged in all of these candidates, our endpoints and all the critical numbers back in F, and we have all the corresponding y values. Now, we're looking only at the y values. The biggest y value is the absolute max. The smallest y value is the absolute minimum. Now, notice how the minimum value of -4/3 occurs twice. That doesn't matter. So we're just strictly looking at size here. We have an absolute minimum, and that's going to be the y value of -4/3, and we have an absolute maximum at the y value of 32 on the interval. Okay, looking here at this next one, we want to find the absolute extrema of f on the interval from -2 to +2. So we need to find our critical numbers. Critical numbers make the derivative equal 0 or undefined. So I need to find my derivative. So I find f prime of x, we'd have to do the quotient rule. Bottom times the derivative of the top minus top times the derivative of the bottom all over bottom squared. All right, so I've simplified my derivative here, and I'm looking. I want to find the values of x that make it equal 0 or undefined. Well, we have a rational function. But if I look at what I have down here, I have x squared plus 1 being squared. There exists no real number of x that I could put in. Squared, add 1 to it, it's going to make 0. So my derivative is going to be continuous everywhere. Or defined everywhere. So now I'm just going to figure out, all right, so since I can't make it undefined, I'm going to figure out what makes it equal to 0. What's going to make it equal to 0 is what makes the top equal 0. So 2 minus 2x squared is equal to 0. And I work my way to solve. That's going to give me 1 is equal to x squared. And x could be either positive or -1. Now we're only looking inside of our interval from -2 to +2. Both positive and -1 lie inside of that interval, so we have to test both of those critical numbers. So what we're going to do is we need to figure out what the function's value is at -2, what the function's value is at each of the critical numbers, so -1 and +1, and what the function's value is at the other endpoint, and compare the sizes of the y values. Okay, so we have all the y values here. Now we're strictly looking for the absolute biggest and the absolute smallest y value. So the absolute largest y value that happens is at 1, y equals 1, and the absolute smallest y value we see is at -1, and so we can identify those. So we have an absolute minimum y value of -1 and an absolute maximum y value of +1 on that interval. So our last existence theorem that we're going to talk about here in this video is the mean value theorem. Now the mean value theorem is often considered by a lot of people to be one of the most important topics or theorems in all of calculus because of its use in proving many of the concepts that you learn throughout calculus. Now, the mean value theorem has some requirements. F has to be continuous on a closed interval and differentiable on the open interval. And if that's the case, so if f is both continuous on the closed interval, differentiable on the open interval, what the mean value theorem guarantees is that there will exist some x value inside the interval from a to b such that the value of the derivative at that x value is equal to the average rate of change. So that's what that is equal to. Now, let's graphically look at this. So I'm going to go back to Desmos and look. And so I have a function in green. And this function in green is going to be continuous and differentiable. So if I'm looking at the green function, I see no breaks in it. It's nice and smooth. It's locally linear. I'm going to have an interval, which are going to be the red dots here. So the red dots are going to be like the endpoints of an interval where I have a function that will be where I'm going to have the endpoints on this closed interval that we're looking at. If we make a secant line, which represents the average rate of change, the slope of the secant line in red is the average rate of change of my green function over the interval, in this case from 1 to, we'll change that to like 3.5-ish. So from 1 to about 3.5, the average rate of change of the green function is the red. It's my secant line. The mean value theorem says that if you're continuous and differentiable on that entire interval, there will exist some x value in between there where the derivative will equal the average rate of change, which means that the slope of the tangent line somewhere will equal the slope of the secant line. And so graphically, if we look at that, and I start dragging and looking and be like, well, where can I make these two be parallel at? And whatever that x value is going to be that point that we're talking about where the instantaneous rate of change equals the average rate of change. All right, so let's look and do some examples here. So let's find all values of c guaranteed by the mean value theorem inside of the given interval. So we have to do some check marks first. So first I need to look and say, all right, we have a closed interval. Is f continuous on that interval? Well, we have a polynomial. A polynomial is going to be continuous for the set of all real numbers. So f is continuous on that domain or on that interval. And I also know that f is going to be differentiable on that open interval because polynomials are locally linear over the set of all real numbers. And in fact, if we wanted to, we could rewrite f. We could distribute that x and say f of x is equal to x to the third minus x squared minus 2x. And if I take the derivative of f, I get 3x squared minus 2x minus 2. And looking at my derivative equation, it is continuous for the set of all real numbers as well. And so f is differentiable. Now, it doesn't have to be continuous and differentiable in all real numbers. It just has to be continuous and differentiable on this given interval. So since those two parts are met, those two requirements, the mean value theorem can be applied, which says that there's going to be somewhere where the derivative equals the average rate of change of the function. So we'll find the average rate of change over the interval. So that's going to be f of 1 minus f of negative 1 over 1 minus negative 1. So we get those y values and we simplify and we get negative 2 minus 0 over 2. So the average rate of change of the function on that interval is equal to negative 1. The mean value theorem guarantees that there will be somewhere on that interval where the derivative is going to equal that value, that average rate of change of negative 1. So we're going to solve for x and see where that happens. So 3x squared minus 2x minus 2, we'll set that equal to negative 1, and we're going to go find the x value. And so we're looking here for this function, and we get two places where it happens. So it happens at negative 1/3, and it happens at 1. Now our answer here, we have to pick the number that lies inside this interval that we tested. So the only number that works inside that interval is negative 1/3. All right, now let's look at this one here. So we got f of x is equal to x plus 5 divided by x minus 1. We want to know what values are guaranteed by the mean value theorem on the interval, in this case, from 0 to 2. So before we jump in and find the average rate of change and the derivative and all that, we need to make sure that f works or meets the two requirements of the mean value theorem, which basically the two requirements are, one, is f of x continuous on that interval, in this case from 0 to 2. And so we're looking, we have a rational function, and looking at my denominator, x cannot equal 1. It's undefined there. And if it's undefined there, it cannot be continuous at 1. When we look at our interval, 1 is inside of this interval. So therefore, f is not continuous on this interval. And if f is not continuous on the interval, then the mean value theorem cannot be applied. So it's important to check the requirements in order for the existence theorems to be applied. The mean value theorem especially, you have to be continuous on the closed interval and differentiable in order to apply the mean value theorem.